Okay, so we're being recorded, so no political commentary here. This whole concept of linearity and saturation and blooming, after reading the student's paper, I realized it's kind of jumbled up with jargon that people with experience use, sort of like doctors use terms that the average person doesn't really understand. And I think the same thing was kind of happening there. So what the idea here is I'll go through the image formation and detection process, and then talk a little about what the detected energy or signal counts are on the final image that you're trying to do science on. So in the most grossest overview, if you imagine that you've got your double star, 2 stars in the sky far, far away, their light comes to us across light years of interstellar medium, and then passes through the Earth's atmosphere and finally reaches your telescope. And the telescope's job is to collect some of that light and form an image on the focal plane. So with any luck, what you see on your focal plane is 2 little dots, and their intensity and relative positions and separations are in a known relationship to the truth out there at the stars in the sky. On the focal plane, let me see, is my pointer work? If you look down here, does the highlighting show up on your screen?
Yes.
Oh, cool. So you've got your star image, but and that's, you think of it as that's the flux of photons that actually hit the focal plane, and that would be normally a fairly smooth function of position. But then the CCD chip is segmented into little teeny pixels, indicated by the vertical and horizontal cross-hatching here. And so at that point, at the detection process, that smooth intensity distribution that's the star image is sampled and then processed by the electronics. So let's start out in the sort of ideal situation where we have 2 stars. They differ in brightness. So star A is bright and star B is a little fainter. But let's assume that those 2 stars are treated equally by the interstellar medium, the atmosphere, the optical effects in our telescope, transmission, absorption, image forming effects. In that case, what you have out there in space, if you could take a perfect image unaffected by the interstellar medium, our atmosphere, any other effects, what you'd see is 2 little points of light, sort of like delta functions in math. And one of them would be brighter than the other, because we said star A is brighter than star B, but they would be infinitesimal in size, but nevertheless giving off flux of photons. After that energy has gone through the telescope, been focused on the focal plane, but not yet detected, focused on the focal plane, it's blurred, but energy conservation says that if I started out with this delta function here, that was star A, after it's been blurred into something that looks maybe sort of like a bell curve, the total number of photons is conserved. And so the area under that point spread function is still a representation of the brightness of the star. Hence, the little bell curve that represents the image of star B, the fainter star, it has the same shape, but it's smaller because we're getting...
Can I ask, the blurring happens by the optics?
not by the atmosphere, or is there a little bit of both?
Yeah, there's a little bit of both. In fact, I think it's on the next page. Good question. The width of that star image, what we call the PSF, the point spread function, is set by the atmospheric blurring, the heat shimmer and twinkling that you see in the atmosphere. It's set by the optical quality of your telescope and also whether it's focused accurately. If you defocus a little, everything gets blurrier, so that point spread function gets smeared out a little further. And some other effects. The key one can be diffraction at the aperture of the telescope, although usually for the kind of CCD imaging that you were doing in this double star project, it's the atmosphere and focus accuracy are the two big effects that set the size of the point spread function. If we take a little closer look at the point spread function and plot the intensity, that might be watts per square meter, or it might be photons per second per square meter on the focal plane. And so you see star A has got its point spread function. There's some maximum intensity level, and usually the size of the point spread function is sort of described by what's called the full width at half maximum. So if you go to whatever the peak intensity in that little blur is, go to half that value and then measure the full width of that intensity distribution. That's the full width half max, and it's a convenient way to describe the size of that blurred star image. Now, if everything is perfect, those assumptions we made about the atmosphere treats both stars the same, the telescope treats both stars the same, then the full width at half maximum of all star images would be identical. So star B has a lower maximum intensity, but if you go to half of that value and measure the full width of the blur, it'll be the same as the full width half max of star A. Now, this is mathematically usually quite true. Sometimes it doesn't look that way when you look at the image of stars on your screen. And the reason for that is imagine that you set the contrast and brightness of your screen display so that it was you were seeing all of the little faintest things in the image. Well, then your what would appear white in your image would be signal levels way down here, and so all of the star images are going to look huge and bloated, but you're going to see all the stars. On the other hand, if you set your screen contrast so that you were viewing just this region of intensity, you'd see a big, broad, maybe sort of circular image of star A, and you might barely see a little dot in star B because you're only seeing this little portion of it. And then if you change your gain and contrast again so that you're only looking at these higher intensity levels, well, star B would have disappeared entirely. And that's all a function of how you adjust the display that you're looking at the image on. Mathematically, in the pixel counts, the full width half max of all images will be pretty much the same. Now, there are effects that can change that. There are a variety of optical aberrations. If you look at a very wide field image, you'll see that everything in the corners is a little blurry and everything in the center is kind of sharp. So the full width at half maximum in the corners could be a little different because sorry?
Oh, sorry. I was just going to say it might also change a little bit with wavelengths if the star is much bluer or redder, maybe.
Oh, absolutely. If you have a spectral filter on your imager, then mostly you're only seeing the colors that are within that spectral filter. Like if you have a V-band filter, then it's only those range of wavelengths. But a really red star and a really blue star might have a little bit size of the point spread function. That's absolutely right. So I think we've talked about if the stars are treated equally by all the blurring effects, then the full width half-lives will be pretty much the same for all stars, and the area under the curve is a measure of the brightness of the star. And if the shapes of those point spread functions are all the same, then the peak intensity is also proportional to the brightness of the star.
Bob? Question for you. Not only would the coma and vignetting have an effect on the edge of the stars, but what kind of role does collimation play in this process? Does bad collimation skew the FMHW diagram?
Absolutely. Imagine if the optics in your telescope are not aligned properly, then you might have a situation where all of the stars are not a circularly symmetric point spread function, but they'll be brighter on one side than on the other. They can even start to look like little seagulls if the collimation is bad, and that's sometimes an important issue. If there's problems in your optics, if you can collect all of the light from that misshapen point spread function, then you're still collecting all of the light that came in from the star. But you may need to use larger and larger measuring apertures because of that distorted point spread function.
I bring it up because I find a lot of times, especially on older observatory images, you often will find the stars are not well collimated.
Yep.
Especially on Newtonian telescopes. They tend to be off a little bit because the little crosses aren't centered on the stars.
Yeah.
So you would be able so would you be able to tell, so a telltale image, if you get back an image from an observatory and you see a bunch of stars, like if the cross isn't centered, that might be a sign of bad collimation if it's true for every star, or if it's only true for one star, then the collimation is probably okay and something else is going on with the star. Is that a good way to test it?
Yeah, that's a pretty good idea. And I think with the modern commercial observatories, you're likely to get quite good images. They'll be well collimated. The fields of view are not very large, and so pretty much all the stars should look the same. And we may come back to that question of what if I have one star that is the center of the point spread function is sort of off to one side. Now, everything we talked about is true of the photon flux, but that exists before we detect it. So let's go back to the view of our focal plane. We have the point spread function on the detector shown here, and then the CCD is divided up into little pixels. And just for convenience, let's look at this row of pixels, and we'll look at a cross section of intensity or signal counts through that point spread function. If the solid black line here is the photon flux, then on each pixel, like say pixel number 2, it's going to integrate that photon flux over the area of the pixel. And then pixel number 3 is going to integrate that smooth bell-shaped curve over the area of pixel number 3. So instead of a smooth curve now, once you've detected the photons, you get this stair-step kind of effect. It's quantized and it's sampled. So that's what actually goes into your image.
A point here to keep in mind, Calais, is that you have on your chip to the side there, you see several pixels above and below the row that Bob has numbered. And so in reality, we're generating a three-dimensional bell curve, if you will. And you often will find that good astronomy software will generate those little three-dimensional mountain peak images. And the sharper that spike is, the better. So we have a real good high signal that way. So it's really a three-dimensional process. This is one cross-section of it. Just imagine this in 3 dimensions.
Okay, and so for the EV projects, there were various photometries that they were modeling this with. I think this is what they were modeling. They had different ways of counting up the photons.
Yes.
Yeah, okay.
Yeah, and well, the photometry is everything we've talked about here is true for photometry also. And in photometry, your goal really is collect all of the signal that came from the star. And so what that means is if on the left side of the picture, if this is my point spread function being sampled, you kind of want to collect all of the signal from all of those pixels, so you're getting everything that came to you from the star, which is the same as saying I want to add up all of the red stair step, all of the signal from all of the pixels that got any energy from the star. And that's what your photometry is trying to do, is collect all that energy. In astrometry, for the double star project, what we're trying to do is use the sampled red stair step data to make the best possible estimate of the centroid of the underlying point spread function, maybe the centroid of that black line bell curve.
Mm-hmm.
And under almost all situations, the centroid of the sample, the centroid of the histogram kind of thing, is the best estimate of the location of the bell curve. Now, what can go wrong? We've been saying if all of the stars are treated equally by the atmosphere and the telescope and everything, now we have to think about how are the photons being treated by the individual pixel on the CCD. And again, at a sort of gross overview, photons come in. This now, the little box represents a single pixel on your CCD camera. So its physical size is a few microns on a side. I think the camera that you were using at LCO GT, the pixels are 9 microns, so they're teeny. So a photon comes in and hits that sensitive area and knocks some electrons free from the silicon in there. Those electrons are swept up by electronics on the CCD chip, and they're stored in a little circuit that you can kind of think of as a bucket that holds all of the electrons that are created on that pixel during the exposure interval. Then at the end of the exposure, there's a circuit that counts how many electrons are in that bucket, and it does that for every pixel on the chip. It counts electrons and then turns it into a number that is usually either called the signal counts or the ADUs, which stands for analog to digital units. So you've got a bunch of electrons in here. Let's call that N sub E is the number of electrons in that bucket for that pixel. And there's a design parameter in the electronics called the gain, which is measured in electrons per ADU. So what you get out of your analog to digital converter is this ADUs, which is the number of electrons divided by the gain. The gain is nominally a constant number. For example, I think on the camera you're using at LCO GT, the gain is almost exactly 1 electron electron per ADU. How many electrons are accumulated? You'll see if you read about the physics of what's going on here. If n photons come in, there's a parameter called the quantum efficiency. N times the quantum efficiency gives you the number of electrons that are created. So if I have 100 photons come in and my quantum efficiency is 30%, I'd end up with 30 electrons in the bucket. And the key thing about that is that's a linear equation. If I double the number of photons coming in, I've doubled the number of electrons collected. And that's really what we mean when we say these sensors are linear sensors.
So that would be doubling exposure time should double photon.
Exactly. Yep. And so that's one of the wonderful things about the CCDs is over pretty broad limits, they are quite accurately linear. In the linear range, as it's called, we'll see on the next graph, the deviation from perfect mathematical linearity is usually less than a percent or so. Unlike in the bad old days of chemical photography with films, if you read anything from that era of the 1930s photometry using glass plates, big deal is what they call the gamma, because in that case the density of the film, which is sort of analogous to the number of electrons collected, is the number of photons in to an exponent, which it describes the response of the chemicals in the film, and translating that back into linear, what's the brightness of the star, is just gigantically awful. So that's one of the reasons CCDs were such a great breakthrough. The other is their quantum efficiency is really high. Quantum efficiency of a modern CCD chip can be 50 to 70%, whereas the quantum efficiency of film was about 2%. So we can go a lot fainter now. Now, all that is still a little bit ideal. Real life. If I did the experiment that Kaylee hinted at, let me have a plain white screen, and I'm going to take an image of it at 1 second exposure, 2 seconds, 3 seconds, and I'm going to plot the signal, say in ADUs, on an individual pixel on the y-axis, and the exposure duration on the x-axis. And as you said, if I double the exposure, I double the number of photons in. So whether I'm plotting photons or exposure time, the graph would look the same. And what the graph will look like is from 0 photons in, a 0 duration exposure, up to some fairly long exposure. That graph will be quite accurately linear. And the slope of the graph is that gain parameter in your chip. But then at some point, the buckets that are collecting the electrons from that pixel start to fill up. And as the bucket gets full, the probability of another electron going in starts to drop. And so you'll see this area where the response is now deviating. It's not linear anymore. It's sort of curving over. And then somewhere along the line, you'll get to where another electron comes in and nothing changes in that bucket because the bucket's full. So here's another view of that same curve. You see the linear range. You may have noticed that at a 0 exposure, 0 photons in, the signal count is not 0. And that happens because even if there are no photons coming in, there is thermal motion of the atoms of silicon in the pixel, and they will, like that thermal motion, occasionally two of those atoms will bump into each other, liberate an electron, and that electron looks just like a photoelectron, so it'll get collected in the bucket. That's one of the reasons that you have a thermoelectric cooler on the chip. I think you were running at either -10 or -20 degrees C chip temperature at LCOGT, because the rate at which thermal electrons are generated is a very strong function of the chip temperature. So cooler temperature, the atoms are not moving around, not jostling as much, and so you get less of these thermal electrons, lower dark current. And the reason that you take a dark frame is you can subtract that out and end up with a curve that starts at 0 and then climbs linearly with the number of photons that came in on that individual pixel. Different CCD designs will act differently as the signal gets larger and the pixels get more full. Some of them will stay quite linear up to a point where they finally say, that's it, I'm full, and then they flatten out. Others have a much more gradual curve. You want your data to always be within the linear range so that it's easy to translate ADUs that you've measured being proportional to the photons that came in. So that's why you want to make sure that your target and your comp stars, lie somewhere in that region. Why do different sensors act a little bit differently on this curve, and what are the effects that set this point at which the signal won't rise no matter how high the photon flux is? And there's a few fundamental effects that describe most of what's going on. The first is that little bucket is about the size of a pixel, so it's a few microns on a side and a few microns thick. There just isn't room for very many electrons in there. So if the bucket is full, and that's called the full well depth of the pixel, usually described in electrons. You might hear a camera described as saying the full well depth is 100,000 electrons. Once you got 100,000 electrons in there, that bucket is full. If I throw another electron in, well, some other electron will bounce out to make room for it, and so the total in the bucket never changes. So that's one reason that this curve flatlines. Even if the bucket isn't full, if the design of the counting circuit, the analog to digital circuit, has a limited range, you might get to the point where that circuit just can't count any higher. As we were talking the other day, if I have a 16-bit counter, the biggest number it can count to is 65,000 and change. So if I have 100,000 electrons, well, the counter can only go to 65,000. Now, normally the CCD designers try to make the limit of the counting circuit and the full well depth about the same. So those two effects kind of happen at the same point in intensity. The third reason that you get this very gradual turnover in signal versus photons is some cameras are designed to do that. They're designed to go nonlinear at relatively modest signal levels. And there's a reason for that. Go back and look at that concept of having a full bucket. So here's here's my bucket. It's collecting electrons that came in from the pixel during the exposure. And if the bucket is full, one more electron comes in, well, some other electron is going to flow over the side because the bucket is full. Where does that extra electron go? Well, one place that it can go is it can fall into the bucket of an adjacent pixel. You know, if in the little sketch here, if this pixel is full, but one more electron comes into it, that electron's going to bounce out, and in the circuitry in that chip, there is usually a preferred direction for the electrons to flow. And so if that direction happens to be up, then that extra electron comes in, somebody gets kicked out of the bucket, and that overflow electron moves into this pixel. Well, what if that pixel is also full or nearly full? Some electron's going to get kicked out of it, and it's going to flow into this pixel, and so on. And what that does is leads to the thing that you frequently see on images where you have a really bright star. A faint star will have a nice round point spread function like that. A brighter star, the point spread function will be more intense. It might look a little broader on the screen. It might no longer be a bell curve. It might be a flat-topped curve because some of those central pixels are getting at or near their maximum capacity. And then at some point, you see pictures like this where you've got a big blob of white light and then a smear of light going up or down or left or right. That's those overflow pixels coming from the overly saturated pixels in the center here. Colloquially referred to as blooming.
Is this a case of herding Schrodinger's cats?
Well, yeah, although I think in this case the electrons are acting much more classically than quantum kind of effects, because they're not disappearing. They're still there. They're just moving into another place. But you see those blooming spikes, and that's the ultimate sign that you have pushed some pixels way too hard. Yes, Kevin?
When you have that graph that's a little bit farther up, there was it might have been you or it might have been Russ or somebody said that they often aim for the brightest pixel in the star to be at peak intensity. On that graph that was, I guess, one more page up, what would be considered the peak intensity here? Would it be where the curve starts to level off or where it flattens?
Yeah, somewhere in there.
Okay.
Yeah, here's the idea. In fact, I think we're going to get to that. Let me.
Okay, yeah, never mind. Sorry,
okay, go up to the sort of histogram looking thing. In a normal star image that is not overstressing any of the pixels, the brightest pixel will be one of these, and it'll be one of those. So think about if you keep that brightest pixel in mind, and let's go back to the linearity curve. If the number of photons or electrons was in this neighborhood, then the signal count of the peak pixel will be whatever that number is. But if I get more and more photons, that peak pixel gets brighter and brighter. At some point, I get into this range where it is no longer true that doubling the number of photons doubles the signal count because the curve is bending over. So your ideal goal is if you look at your target stars and your comparison stars, any stars in the image that are of interest to you, the peak pixel of those of the brightest of those stars should be somewhere below the turnover point. If we're on the lower dashed curve, you'd want to be down here. If your sensor happens to operate on the upper dash curve somewhere here, you want to stay away from the regions where you're nonlinear, because that'll distort all of your calculations of centroids and photometry. Mm-hmm. That makes sense?
Yeah.
Now, why would some cameras be designed for a fairly broad range of non-linearity? It has to do with this bucket overflow problem and the blooming problem. And so on the next page 6, back to the question, bucket is full, one more electron comes in, so some other electron is kicked out. Where does it go? Well, the other option is have a special circuit that's designed to capture those overflow electrons so they don't get into the image that you're detecting. And that circuit is frequently called an anti-blooming gate. When the buckets start to get full, that circuit sweeps off the overflow electrons, puts them in a separate holding area so they don't flow over into the adjacent pixels. Good news is that largely eliminates the blooming effect, hence the term anti-blooming. The bad news is it reduces the linear range. So in a non-anti-blooming sensor, you will typically have, if you plot signal versus photons in, you have a curve that is very nice straight line until it thresholds and goes flat. Whereas in your anti-blooming sensors, somewhere typically around 50% of the full well depth, that curve starts to go nonlinear, turn over, and slowly climb toward saturation. What that means is your dynamic range is reduced. I have to set my exposures so that my stars fall somewhere in this linear range, if I can draw that. Whereas on a non-anti-blooming sensor, I could have a wider range of brightness or exposure. But you can use both sensors. The trick is characterize the sensor you're using so you know what the limit of the linear range is, and then pick your exposures so that your stars of interest, their peak pixels, are within the linear range.
Gotcha. So in order to experimentally tell what kind of sensor you're dealing with, you would take a large number of exposures and plot the peak pixel into the peak pixel counts for that sensor, and then based on the shape of the curve, you could infer where the linear range is?
Exactly right.
Okay.
Exactly right. You're basically trying to plot out this curve, and the students did that for their double star project. I think they may have misinterpreted it a little, but they did the work. What is it that you take a picture of? You ask that question at a group of astrometry or photometry guys, and you'll generate 5 answers and 6 arguments. You can look at stars, pick a star, and look at the single brightest pixel in it, and then do that at longer and longer exposures and plot the curve out. Or you can look at the star and count up all of the signal from all of the pixels that have that starlight on them and do the same thing. Or you can, if you're taking flat frames, just a white screen, you can actually use that and take a series of exposures at different durations and plot the brightness on your flat field as a function of exposure, and what you'll see is this kind of a curve. It'll go up linearly for a while, and then at some point it'll deviate from linearity, and now you know that this is the ADU level that marks the greatest signal that I can deal with and still be in the linear range. There are
Calais was that Ed Wiley did was done with a white screen. That's how he did his, with a white screen and varying exposure types. That's how I describe it. How he did his.
That's cool. I don't know how to request that from the robotic telescopes, so I think we'll probably have to go with the peak pixel thing. Though they did it for the integrated counts, not for the peak pixel ones, which we should.
Right. But you've got the images.
Yeah, we have the images. We can do it.
So you could go back and do it. Now, and there are good points and bad points about all of those options. You know, the peak pixel on a star, or the integrated image of a star, or the flat screen. Probably the biggest disadvantage of using the flat field screen is what you said. I'm not sure I can request that from my robotic observatory. If it's my observatory in my backyard, I can do that and squander telescope time that way. But let's talk a little bit about the measuring the linearity and the difference between looking at the peak pixel versus the integrated signal. If I'm in the linear range, so that ADUs out and photons in are in a linear proportion, and the black line here is the point spread function, and the red hash marks are the sampled pixel by pixel data that you actually get. The peak brightness pixel is pretty close to having the same intensity as the peak of the actual photon flux curve. Pretty close. Unfortunately, what happens, especially in images where the star images are really small on your LCO GT, you know, their full width half max is only 1.5 or 2 pixels, and so what that means is you may get, here's pixel here, collects that light. The next pixel collects that light. Well, okay, that's capturing the peak of the curve pretty well, and then the next pixel captures this stuff. In which case, your peak pixel and the peak flux are pretty closely related. The bad thing happens is in the next image, let's say the star is shifted by half a pixel. And so now I've got pixel number 1 is collecting this light. Man, I got all this low signal on this side of the pixel and the high signal here. So the net is going to be, down somewhere here. And then the next pixel is grabbing all of this light. And again, it's got the brightest part, but also some fairly dim parts of the point spread function. And so the measured, detected brightness of the peak pixel can bounce up and down noticeably, depending on whether the point spread function is centered on the middle pixel or if it's sort of shared between 2 adjacent pixels.
Gotcha. I'm just wondering, which images do you mean? I can't remember any images where it was that small, but maybe.
I'll pull one up. I'll pull one up when we're done. I was actually surprised how small the point spread function is, and part of it is because you were doing 2x2 binning, which seems to be the default position at LCO GT. I don't think it's a problem, but it makes the point spread functions teenier. Anyhow, if you're going to do your linearity plot based on searching for the brightest pixel in the star image, you will get some scatter because of that sampling effect. So what my recommendation there is, ideally you have 3 to 5 images at each exposure duration. You look at the peak pixels and you'll see there's a range of value at a 1 second exposure and another range of value at a 2 second exposure, but you can kind of eyeball a straight line through those and you'll be able to tell when it's starting to deviate from linearity. The alternative approach is to say I'm going to measure the total signal in the star image. And the thing about doing that is let's consider a point spread function that's a little bit saturated. So the black dashed line is the photon flux, but these pixels that are near the peak of the curve, their wells are full, or we've moved pretty firmly into the nonlinear range of the sensor, and so the brightest pixel is no longer a representation of the brightest portion of the point spread function. Well, but we're saying we're going to measure the whole integrated signal, so we're going to add up. We're going to add up all of that, and if you do that, you will see the curve is linear at short exposures, and then it'll turn over. The only thing is that if you look at the total integrated signal in the star, it's less sensitive to the onset of nonlinearity, because you've collected all of this light and you're only missing a little bit, and so your curve only tips over a little bit, even though these central few pixels might be pretty noticeably in the nonlinear range. And that's why I kind of prefer to use the peak pixel approach.
Gotcha. That makes sense.
Now, now how does this affect astrometry? Remember, in the double star project, we've got this curve of photon flux versus position. We've sampled it, so we're seeing pixel by pixel data points. We're going to take the centroid of the red histogram and use that as the best estimate of the centroid of the photon flux. And if we look at that image that's a little bit saturated, there might be a little effect, but probably not much, as long as the underlying photon flux is a nice circularly symmetric point spread function. So a little bit of saturation under those conditions is probably not disastrous. But even though we usually think of the point spread function as being smooth and circularly symmetric like a bell curve, it often is not at some level of accuracy. Like Richard mentioned, that if my collimation is bad, my point spread function is going to be sort of skewed to one side. It's going to be asymmetric, as shown here. If there's a little coma, the left-hand side of the point spread function has a very gradual rise in brightness, and then the right-hand side has a very rapid fall-off, typical of coma.
What's a coma?
It's an optical aberration in the telescope optics. Okay. And there's a whole lot of those kind of aberrations that can give you a little bit of a non-symmetric point spread function. And frequently it won't show up if you're just sort of looking at the picture. Everything still looks kind of round, but it's really in there. So you would still say that my best estimate of the location of the star is the centroid of the photon flux, the black curve, and so that centroid is here at the dashed vertical line in black. But suppose that my sensor is saturated, so starting at the left-hand side of the point spread function, and the signal gets brighter and brighter and brighter, and at this point my pixels are saturated. And so brighter, more photons in no longer means more ADUs. And so I get this flat-topped, detected signal. The flat top is diagnostic of some sort of saturation has happened. And it turns out if you calculate the centroid of those little points, that centroid is noticeably to the left of the centroid of the true photon flux. And so you're no longer measuring a good representation of the location of the star.
Calais.
Pardon me?
A simple test we used to do in the field for coma, and it's easy to do, is we defocus the stars a little bit and look at the stars near the edge of the field. If they become fan-shaped, the telescope has coma. There are corrections you can get to correct for coma correction lenses and stuff. But that's how you tell it. If you're slightly out of focus and the stars near the edge take on a fan or wedge-shaped appearance rather than round, you probably have coma, and that may affect your images then because of that. That's something you can maybe run a test on sometime with one of these scopes. Ask them to defocus a little bit, shoot an image that way, compare the two images. Otherwise, if they have coma, you have to have corrections in there to correct it, and it's probably not going to be available to you.
Well, so this centroid here, the dashed gray line, even despite the fact that there's some coma in the optics, we would say that that dashed gray line is more representative of your centroid?
Yeah.
Than red? I see.
Yeah, it's still, although it's distorted, it's still the best representation of the location of the star. And because in your double star project, the two stars are close together, chances are their 2-point spread functions are affected identically by whatever the optical aberration is. And so both of them would have that same, kind of asymmetric point spread function. But when you're measuring the separation between the two of them, well, the distance between the two centroids is still the best estimate of their separation, as long as you're not on the red dots with the flat top.
I'm just wondering if, since they're equally bright, approximately, they're very, very close, within like 0.1 magnitude units, then would you expect them to be affected by that red in the same way as well?
Yeah, probably. But it doesn't take much difference in brightness to move the centroid differently because of that saturation effect. As long as you're in the linear range, then the centroid calculations will be equal between the two stars. But if they're even a 1/10 or 2/10 of a magnitude different, so one of them saturates here, and the next one saturates here, well, now you're going to calculate two different centroids.
Mm-hmm.
So I kind of don't like that idea. How big the effect is well, you could probably do a whole science project on that, and the answer will always come out better that you stay in the linear range. Your star images seem to be pretty round, but as in anything, you don't know how much coma there might be, and you can be absolutely positive that however well you have focused, it's not infinitely perfect. And however well the telescope is aligned, it's not infinitely perfect. And so there's always going to be a little of this in any image. Hence, better to be in the linear range. And that's why you take the time on one run with the telescope and camera you're using to measure what's the linear range of the CCD, and how many ADUs can you collect on a pixel before you go nonlinear. I think usually people say if I know the linearity range in ADUs, I try to have the peak pixel in my brightest star of interest about 80% of that, and the 80% is strictly a safety factor. So if the air gets a little clearer or something like that, I know that I'm not bumping into the nonlinear range. And we talked about why I kind of prefer plotting the linearity curve using the peak pixel rather than the integrated ADUs.
Once you know the linearity range, like from this project, if we go back and we do the multiple exposures, and we have it for these stars in this telescope, would we be able to use that for a different set of stars that have different brightnesses? Or should it
absolutely. Ideally? No, absolutely, yes. Let me scroll back. This linearity curve, wherever the curve starts to turn over, that number of ADUs is a characteristic of the CCD. And so then you can say forever after, I know that my linearity limit is that many ADUs. Keep the peak pixel of stars of interest below that or below 80% of that.
Nice.
Just always check the fit setter to make sure they have not changed the camera on you in your last run.
Yeah. Okay.
Yeah. That happens, and so anyhow, the kids did exactly the right thing in this graph. My preference would be to use peak pixel, but the other thing is I think they probably got a little aggressive in saying that the 20-second exposure was still within the linear range. To my eye, we're starting to deviate somewhere between 10 and 20 seconds. And my guess is that the 10-second exposures, and I don't remember what filter and all that is, would probably be a little safer.
Okay.
But you can confirm that, and because your star images seem pretty good, they're nice and symmetrical, and because astrometry can be a little forgiving of a little bit of saturation, you might find that when you run your astrometry for the 10-second exposures or even the 5-second exposures, it's not noticeably different from what you did at 20 seconds.
We don't have multiple. We only have those 3 images. I mean, we'd have to request some more, which we can do, but we only have those 3 images of those stars because we only requested 1 per exposure time. And then we did actually request a bunch more at the 10-second exposure time and got them back. But it was just a function of the moon. There was a full moon that night, and the 10-second ones were saturated. Because the ones that we had at multiple exposure times were in the there was a new moon, and so then we were just like, well, this didn't work out. I mean, we can request more. We can certainly do that. The 20-second exposures did seem to agree with they were very consistent with the historical measurements, but so were even the ones that were ballooned. Maybe because their centroids were shifted in the same direction or something, but we would certainly want to use ones that we had good confidence in.
Yeah. I hate to send you back to get more data at this point, but if that's doable in the time that you have available, probably that would be the most ideal. The other hand is take a look at the.
I might end up just doing it myself because the kids are going to be dispersing for summer soon.
Right. But take the 20-second exposures and try to plot the point spread function, in ADUs versus pixel number as a 3-dimensional graph, and see how bad is the flat top. If it's not too bad, then this is probably still usable data.
Okay, yeah, that's a good idea. So make a 3D plot. That would be potentially cool. That would be fun.
I don't know if you have it available to you or not, but I use Maxim DL to process my images, and Maxim will generate that graph for you.
Oh, that's cool. Yeah, no, I don't have that one, unfortunately. We sort of have a we restrict ourselves to free software where we can.
You always file it by hand. It's always possible to do it by hand.
Yeah, if the software will spit out a matrix of X position, Y position, and intensity, ADUs, then you can always import it into some spreadsheet and make a 3D graph.
Yeah, very nice. Yeah, we might do that just for the experience of doing it. And then also we could potentially maybe use those images.
It'd at least give you a way of assessing how significant the saturation effect is, and it may not be badly affecting your separation and position angle measurements, because you've got the good situation. The stars are about the same brightness. The point spread functions seem to be nicely symmetrically symmetrical or radially symmetrical. So a little bit of saturation may not be the kiss of death here. Plus, your measurements do seem consistent with history, and they show the stars moving in the expected direction.
Cool. Could we pull up a couple of those images that you said were only a couple pixels wide, if you have them?
I have to change something here. Share my screen to AIP. Okay, this is a piece of software called Astronomical Image Processing, which is not free, but as you guys get more and more into photometry, it's a very neat program. It's about I think $100 or $150, but it comes with one of the best photometry books. It's included with the software. It's by Richard Berry. It's really, really good. Anyhow, you will recognize. Do you see the image on your screen? Okay, you will recognize this picture as one of your eclipsing binary pictures, although it displays upside down on my screen. And if I click on your target star here, what the graph is showing is ADU count versus radial position from the centroid. And the first heavy line is 6 pixels radius, which was the measuring aperture that your eclipsing binary team used, and then the 9 pixel gap, and then the 15 pixel radius for the sky annulus. And you can see, the point spread function is quite sharply peaked, and it's gone from max down to practically the sky level in a couple of pixels.
Wow. Yeah. The images look, just visually, they look like they're wider than that when I blow up the thing on the screen. But I guess maybe that's a function of how you set the contrast or something.
Exactly. If let me see, I think I can. Yeah, if I start messing with the contrast, those images are getting smaller and smaller and smaller as I set a higher and higher threshold.
I see.
And let's see, now I don't know how to go back. And I noticed that I don't see it as a problem. Let me pull up another tool here, the star image tool. And so if I click on that same star, which was your target for the EB project, full width half maximum is 2.3 pixels, which is barely sufficient sampling. You need minimum of 2, and I think most people would prefer 4 pixels across the full width half max to make sure that you're completely sampling the point spread function.
And that, the full width at half maximum, though, is not ideally anyway a function of exposure time, right?
Correct. Yeah, and it should be the same for all stars at whatever exposure. This is a 150-second exposure in B band. So, let's see, if I pick another star like this guy down here, let's see, we were at a full width half max of 2.3, and I hit this guy, it's 2.4. They're within 10% of each other. That's pretty good. Whereas, if I go over to this really bright guy, 2 things will happen. First is the full width half max is now 3 pixels, and you may not be able to see the shape graph very well, but it's got a flat top. That guy is saturated. It's not what you're using for a comp star, so it doesn't matter. That shows you what happens when you have a saturated image. You get a flat top, and you get a wider than normal full width half max.
Mm-hmm. Is that what was wrong with comps 3 and 4 though?
Yeah, that's what I was saying. Is the full width half max got large. I'm not sure how to interpret the guideline you were given about the peak value or integrated ADU limit. It may be absolutely correct. The thing that was spooking me is these images were binned 2 by 2 on the chip when the image was being taken, and there's good reasons that people sometimes do that. But the thing is, that means you've got 4 pixels that are leading to a single output number. If one of those 4 is saturated, you'll never know.
I see.
And it may or may not have an important effect, but it looked to me like those 3 of those comp stars that were originally used, I was seeing these larger than normal full width half max, so it's a broader than normal point spread function, normal being the typical star in the field. And the other was when I started plotting comp 1 minus comp 2, I saw a lot of scatter related to those, and that's often diagnostic of somebody got saturated.
Okay.
Or something else went wrong with that comp star.
Yeah. Or it was right. Or it was close to that bright one. Yeah, it's really hard. Like I was staring at these last night when I look at the graphs of the comps versus each other, and at one point they were trying to do R squared, about like they were fitting that line of the. But of course it's 0 because they're not supposed to be correlated.
Well, but the difference, either the flux ratio comp 1 divided by comp 2 or the magnitude difference comp 1 minus comp 2 should be a constant.
Yeah, no, that's what we were looking for. But in essentially what we ended up doing was looking at the standard deviation of that number,
right.
Looking for the lowest standard deviation of that ratio, and also the lowest slope of that. Like when we did fit a line to it, the lowest slope, so that it would be as close to flat as possible.
Yep.
And it's really hard because, like, you look at those graphs. I don't know if you were able to see that collaboratory. They like you see a whole bunch of flat lines with some scatter, and then if you do see a slant, you have a hard time telling like whose fault it is. Like is this like which comp star is to blame for this slant? And you can sort of back that out a little bit can show you some of the plots, or I don't know if I can.
Yeah, I couldn't open that. In Internet Explorer, I got a message that said go try Chrome, and in Chrome it just said I don't get this. So it may be my old software.
Yeah, it's supposed to be browser based, but maybe it's not. Is it possible for me to share my screen? You can.
Yeah, I can make that happen.